So our topic today is, does the tube amplifier have a place in the modern listener's collection? Does it justify its weight? Does it justify its heat? Does it justify its price? Especially when you can get a $500 topping A90 that measures super well and it sounds good enough. So this in a way was a misgiving title, because if you ask me, 2022's CanJam being generational, the solid states have been what was pushing forward the state of the art in amplification. In the last 3 years, very, very highly touted, you've had something called feed-forward technology, branded under THX. You have had NFCA, which stands for Nested Feedback Composite Amplifier. A lot of Chinese companies are starting to use that. And then you have all sorts of low distortion, high power amplifiers that can really push power into hard to drive headphones. And at the same time, actually address in part some of the criticisms of solid state. One of the few remaining reasons why someone might use a tube is because a tube sounds a bit more natural, a bit more warm and inviting. Solid states are starting to do that now. So the barrier, the gap is starting to close in that sense. But before we get to tubes, I think we can understand tubes better in the context of solid states. And so this first part of the conversation will discuss solid states as we know them today. So they are cool solid states because today they satisfy both the objectivists and subjectivists. Since 2019, I think we've had access to all sorts of measurements and graphs online, both accredited by journalists or just forum users using test gear to measure the amplifiers, and they're all super. A lot of them, well, quite a few of them use the nested feedback technology, a lot of feedback to gain those numbers, and they're very impressive from the start, and they actually hold up well under critical listening as well. But in that, we also fall under the habit of listening with our eyes as much as with our ears. The numbers do condition, I think, some of the way we react to hearing a solid-state amp sound that we know measures super well. It's actually one of the reasons why reviewers from magazines, they write their review first before actually measuring the amplifier and then publishing it as a footer in the back of their review. In any case, yeah, I would say I would want to acknowledge how solid-state amps have kind of fulfilled the engineer's dream of getting something that is objectively perfect and still delivering on sound quality, a balance that had been a struggle to achieve before this, and doing so at an affordable price. So we go on still talking about solid states, okay? There are affordable solid-state amplifiers, the i5 Zendak, the topping A90, some from SMSL, a lot of Chinese brands we know about. But the truth is, before we go into tubes, there are expensive solid-state amplifiers as well. So how do we abide their presence? How do we actually consider them as an option when the surprising thing is a lot of high-end solid-state amplifiers don't measure as well as these miracles from China that are doing so at $500. It's a big question because is a measurement that important in the first place? And now we start to look at the validity of certain measurements in trying to judge how good an amplifier sounds. It's the same conversation that some of you might have been exposed to when we were talking about IEMs just now, and how measurements don't tell the full story, and we still need to complete our research and development in that sense. The thing is, bad measurements don't always mean it's badly engineered. The thing with high-end solid-state amplifiers is people still buy them because they do sound good, they do sound better, despite a machine telling you they don't do as well. I can think of the Ferrum OOR of late, made in Poland. Expensive solid-state amplifier, definitely more than Chinese product. And probably doesn't measure as well as a topping, but everyone seems to like it, so that's good. Why does it actually sound better, or what does it have a case for charging triple of what in A90 does? So let's break down then how cheaper solid-state amplifiers are built and how they achieve these mad numbers. They use, for the most part, something we call op-amps, and these op-amps are called integrated circuits. So they're little chips that are available on the mass market that can be bought easily from factories, product lines, and they just need to be installed via a data sheet. There are formulas to then get them to perform and achieve those distortion figures, those noise figures. The thing with ICs, these solid-state op-amps, an ideal one was something we call infinite gain, which means whatever goes in comes out extremely larger. Some of these may not just be for audio. Of course, there are other applications that really use these op-amps to, in the intended way, but without considering that they have a sound as well in an audio application. So when you have this infinite gain, or at least very, very high gain, you need to do something, and that's called close the feedback loop, close the loop, and this sends some of the gain back into other stages. It's a form, inadvertently, error correction. So when you error correct, you're going to push down the distortion numbers. You're going to get really quiet performance sometimes. And other benefits do happen, right? These things do sound good. So sometimes frequency extension at the extremes also goes up, and you have something called low output impedance, which helps you deliver power into varying impedance loads as a headphone or an earphone. So the thing is with these, right? So the instant noodle analogy I used while describing earphones just now, op-amps, that would be the parallel. You have a packet of seasoning, you have pre-cooked noodles, you add hot water, and 90% of the time, each cup of Nissim will taste the same as the next one, and you will keep making them, and they taste good as well, don't they? But same thing, can we actually compare Nissin to gourmet pasta that we cook ourselves, and we go through the entire process of sourcing the ingredients, choosing the recipe, making the right adjustments in terms of balance, salt, pepper, whatever. If you do it right, this effort from scratch typically does sound a bit better. I mean, does taste a bit better, you see. Same applies to sound. So what solid-state amplifier that's high-end and costs a bit more might have is called a discrete circuit, in which rather than pick an IC off a manufacturing line that was pre-created for all sorts of purposes, audio among them, they choose individual transistors with which the ICs are built, but then they build their own circuit with it. Okay, everyone following me so far? Cool. So if you have any questions, please stop me. This is quite a quick introduction to amplifier building. So the issue with this gourmet pasta, it costs more to make because pasta and salt and olive oil and whatever, they cost more than a Nissin alone. It takes more effort, it takes more time to perfect your cooking skills, it takes more consistency to get everything tasting the same with each effort. And so these restaurant chefs, they do that all the time. Same thing, same analogy, I think it's a very good one to a solid-state amplifier builder who wants to build the best circuit. The key with this kind of circuit is that you can control the amount of feedback you use. So a circuit that's designed discretely means that you have a certain amount of gain. Gain being what goes in comes out bigger. You can keep that low. Generally speaking, I as a member of trade try to advise people to choose low gain devices, or if they have a choice, to only employ low gain, especially when it comes to using a music player or a DAP, something that you want to get your volume as high as possible for signal to noise performance. I'll get at that in a bit. So whatever I've said, exchange the solid state, high-end, expensive amplifier in your mind for a tube amplifier now, and the same argument applies. So we've established that a high-end solid-state amplifier costs more because it gives you more than a cheap amplifier. So you take said solid-state amplifier and then you put it now next to a tube amplifier that costs about the same amount of money, the same amount of work went to it. It's about the same price or slightly more. Then we ask ourselves now, since they are equal in quality, just sounded different, why are tubes better than solid states in some situations? The first thing we talk about is a distortion characteristic. Now, when you amplify a signal, there's always going to be distortion. No matter how small, what goes into the amplifier comes out slightly different. This difference in gain is what we call distortion. But like measurements, not all distortion is equal. There are desirable distortions to the human ear. We had Bram just now, a friend of Zepp, discuss why a dynamic driver sounded sometimes more pleasing to people than a balanced armature. He said that it emphasized the second harmonic over the third harmonic. And so a harmonic would be the initial event happening at perhaps 1 kilohertz, and even an order harmonic will happen at 2 kilohertz, but an odd order harmonic will occur at 3 kilohertz. All following me? So odd multiples, even multiples. And then what happens beyond the second and third? There are actually much higher order distortions, 5th, 6th, 7th, 8th. This is where the distortions start getting actually really bad. It's actually what we hear the most of. This is what we call intermodulation distortion, in which various harmonics, 2nd, 3rd, 4th, 5th, start blending with each other and creating a sound, an artifact that is perceptible to the human brain, maybe not audibly, but to a machine it will be there. To the human brain, very subconsciously, it will still be there. And so, doing this, well, I guess it's musical. It sounds like part of the event, right? That me tapping the can versus doing this. It's a very different sound, and it sounds nothing like tapping the can. Very crude analogy, but it's that effect. This is what we call intermodulation distortion, high-order distortion that you unfortunately cannot help hearing. The cool thing about tubes is that the circuit tends to be simpler. And with simpler circuits, one of the byproducts is a simpler order distortion. If there is distortion, we want to have as little as possible. We also want to have it as low order as possible. Tubes, single-ended tubes, which is what the 300B is, usually produce a second harmonic distortion, a even harmonic distortion, which is why we equate tubes to warm sound, but there's more to that, I'll get to it. Whereas a solid state, depending on the implementation, and some tubes actually can produce a odd harmonic distortion, which people in listening tests actually equate to being cold, dynamic, honest. Not a bad thing, but maybe not what you buy a tube for, okay? So that's a generalization and overview of distortion characteristic. If there is distortion, keep it as low as possible, keep it as little as possible. And then we talk about a tube. Does anyone know the definition of a tube over here and what it actually is doing as part of an amplifying circuit? Okay, so a tube is an old way of getting charged particles to one location. Basically, it's a way of energy transfer. And you have in a vacuum filaments that heat up particles, electrons, whatever, and then they jump the poles in the vacuum, and then they flow. Okay? Now, the thing with tubes is that they're like a tap. You tickle them with a bit of something called voltage. Voltage is sound, and then they let current flow through them as well, and voltage plus current equal to power, whatever application you're doing. So solid-state transistors are also like that. They have, you tickle them with a bit of voltage that comes in, and then they let current from the power supply through to whatever you want to drive. Clear so far? They do the same thing, they just do it differently. One of the things that they do differently is that a tube, being filaments suspended in a vacuum, because you do not want to let air in there, they'll burn out, is that when you have a vacuum, there's something called very low capacitance in the device. We call these amplifying devices. So when you have low capacitance, unlike a solid-state transistor, you actually find yourself having less compressive intermodulation. That's a fancy word for tubes just sounding a bit more immersive sometimes, tubes having a more natural presentation of space, less forced, a little bit more liquid and flowing, versus a solid state that's actually trying to drive the transistor's capacitance. So when you do that, the amplifier works harder, and then distortions can happen, and they can quickly get out of control.
Yes. So you are trying to say that this difference in experience there's a scientific term to it, right? What was the technical term that you were saying just now?
Okay. So capacitance in circuits is a form of resistance, not purely resistance, but a simple way of understanding would be the amplifier within needs a little amplifier to drive it also. So within the power plant, there are power plants. You see what I mean? Okay. Capacitance, yes. So if there's a lot of capacitance in the circuit, which solid states have by nature of the transistor, they are going to take more effort from the amplifier. Higher order intermodulation can occur, and a lot of the effects are what we would describe as compressive. Compressive being high frequencies are inhibited. Okay, no worries. We can talk after this if you need more notes. I'll be happy to. No problem. No, you take your time. If you need me to stop, just let me know. And as a segue, it is in this case, you'll be surprised. Tubes are extremely transparent as high-frequency amplifiers. They let high frequencies flow very easily because of this lack of capacitance. And so you will see tubes today in satellites, in microwave, industrial microwaves, because of this lack of capacitance. They go to space. And transistors are a newer thing than tubes. I think they came out 20 years later. Okay, maybe a bit more than 20 years. And they're playing catch-up. Transistors are playing catch-up to tubes in this capacitance sense. You could get a transistor to do what a tube does in space or in a microwave today, but it will cost a lot more money. It may not be as reliable. It may not be as effective still. So not just in audio, this is 1920 technology. And it shows like audio is a bit timeless because we wouldn't be using Nokia 3310s today. We're using iPhones. They cost the same amount of money as a 3310, but the iPhone is undoubtedly superior. We can't say that in audio. Transistors are good for one thing. Tubes are good in another. Phase reproduction, it's what I also covered briefly when talking about IEMs. When you have an extended frequency response that's flat, and the amplifying goal is to have a flat frequency response, unlike perhaps an IEM that adds color and then gives you the sound because of its characteristic. Your amplifier is desired to be as neutral as possible, as extended as possible, because what happens at 40 kilohertz, 70 kilohertz in the tube passes through at 20 and will infect there. If you have a solid-state amplifier that dips at maybe 40 kilohertz, the phase starts falling off, phase being the timing of the arrival of signal to your ear, and then things start sounding a bit confused. Whereas if we can keep this straight up and going on further, then maybe this audible effect of phase confusion happens at 30 kilohertz, beyond the human hearing range. Roughly clear? Roughly clear? So that's why a tube also is transparent. I think audibly you do hear a difference in tubes just sounding less forced. The clarity is easy, it flows to you in a natural way. There's a lot more to designing a good tube amp than a tube, but it's a start, and this is why engineers might build that tube, because it gives them more possibility to achieve what they want. Okay? High linearity. One of the reasons tube amplifiers can be very big and very hot and very heavy is because they do things the old way, and there's no other way to use a tube in a modern application than the old way, which would be a very big power supply and something we call bias to keep the tube turned on in its optimal state, so that when voltage goes into the tube, current flows as it should to give you power. Complicated to perceive, I understand, but bear with me. The idea of linearity is whatever goes into the tube or the amplifier must come out the same. Input must equal to output. And in that sense, tubes are a bit better because they have something we call a high operating voltage to begin with. When a solid-state transistor amplifier gets operated, it runs at maybe 30 volts, maybe 60 sometimes. Whereas the usual operating voltage of a tube is 100 volts, 200 volts, beyond maybe sometimes. And when you have this kind of number, think of it literally in terms of sweet spot. When 10% of your tube is linear, where what you feed in comes out the same, then when you have 100 volt operating voltage, 10% is 10 volts, but 10% of 30 volts is, someone do it, 3 volts. So you can see how much easier it is to nail linearity of a tube in that sense. Same thing with bias. Tubes usually need to be run at a very stable condition. So class A is a very typical thing with tubes. Class A is horribly inefficient. It gives you about 20% of what it takes from the wall. Apart from that, it gets turned to heat. But that pays off in audible result because that again stretches the sweet spot, and it becomes easier for the engineer to design a good circuit around a tube, provided he does the groundwork. Big power supply, big heat sinks, and things like that. You know, the funny thing is when we work in high-end audio and a device breaks down on us and we replace it for the customer, the company replaces it for the customer, they always ask us for the thing back. And you'll be surprised that it's not the PCB they want, it's the chassis, it's the transformer, it's the heat sinks, the significant pieces of metal work that actually cost money to build. And so that's why also parts cost is quite expensive in a tube. Metal chassis, big transformer, big power supply, all these things play a part. Yeah. Roughly understand the linearity, guys? Okay. Just stop me again if you all need. So this matter again, where we want to use a tube. So things like the 300B, okay, are power amplifiers, right? They use tubes to give you power as well, meaning that that's driving the headphone directly sometimes. Most of the time it's driving something we call an output transformer, but a tube is driving the headphone, okay? There are some amplifiers that rely on tubes in the front only, but what's driving your what's driving your headphone is a transistor. It's a hybrid tube amplifier. Best of both worlds again. Some trade-offs, but more compact, cheaper to build, smaller, less hot, less involved. Okay, so this all matters in when it comes to deciding what kind of tube amplifier to build. The 300B is a rather extreme case of a headphone amplifier. 30 kg, 2 chassis, and runs very hot. But if you guys hear it, I hear a lot of people like it already, so I can't wait to try it later. Weight and size, yeah, that's been explained. There is no way you can miniaturize a full-size tube. The closest we've come is something called the new tube and little walkie-talkie tubes that they used back in the day in the military to, run their radios and things like that. But running a big 300B amplifier and things like that on the go, not going to happen. In today's energy-conscious world, Class A amplifier also may be frowned upon, depending on where you live. With this, we come back again to cost. Why certain amplifiers cost a lot of money? They cost a lot of money because they rely on audio fundamentals, which would be the original basics back in the 50s and 60s. There are no shortcuts around them, sadly. Feedback typically doesn't sound very good, can be bypassed, but still will give you the nasties of feedback. If you want to do a feedback-free amplifier, you can build your own discrete circuit, but that will also lead to parts costs and things like that, and it won't measure as well, almost certainly. Lastly, if a tube, there's feedback, but the interesting thing about tube feedback is that the way you wire up the little pins in the cathodes and the anodes in the tube usually lead to lower order harmonic distortion, meaning the feedback isn't going to give you as audible and irritating a form of distortion that you might get from a solid state. So the key in, also, audition first. Drawbacks of a tube amplifier, we've talked up all the sonic advantages, is they sound really good, but in some cases may not. A tube is fundamentally a high voltage, low current device. To be able to feed your headphone directly, like in the case of CanJam 300B, you have to pass through a transformer first, that hunk of iron that you wind wire around. What it does is literally transform that tube from being high voltage, low current, to high current, low voltage for headphones that they need. This extra work also means that there's more effort going into it, meaning if your headphone is very low impedance, like 16 ohms or something, may not sound as good. You got to try it. So synergy is quite important with tube amplifiers. I had someone who tried a ZMF Atrium just now with a solid-state amplifier. According to him, it sounded really bad. When he switched to the CanJam 300B, it worked very well. So synergy, again, plays a part. I can also see the same process repeating, in which someone plugged in a non-optimal headphone into the 300B and it failed. So in that case, solid states typically fare a bit better in more use cases because they apply themselves a bit better to a wide range of headphones that could be plugged into them. Okay, and that brings me to the end of the seminar. It's very technical. Thank you for bearing with me.